Welcome, everyone. I'm excited to kick off our presentation today. The topic is real numbers, and this is our very first slide, the cover slide. In this presentation, we'll explore what real numbers are, their properties, and how they're used in mathematics. So, let's get started and dive into the fascinating world of real numbers. All right, let's take a quick look at the contents of this presentation. We're going to explore different types of real numbers today, starting with the basics and then moving into more specific categories. We'll begin with natural numbers, which are the counting numbers we use every day. Then, we'll look at whole numbers, which include 0 along with natural numbers. Next, we'll cover integers, which add in the negative numbers. From there, we'll delve into rational numbers, those that can be expressed as fractions, and irrational numbers, which cannot be written as simple fractions. We'll also see some practical examples and practice problems to help solidify these concepts. Later, we'll explore operations with these numbers, like multiplying, dividing, adding, and subtracting integers, including understanding additive inverses. Throughout the presentation, I'll connect these concepts to show how they all fit into the larger idea of real numbers, which form the foundation for much of mathematics. Let's talk about real numbers. Real numbers are essentially every number you can imagine. Think about the number line we often see in math class. Any point you can mark on that line represents a real number. This means that real numbers include all sorts of numbers, whole numbers, decimals, fractions, and even irrational numbers like pi or square root 2. When we say that real numbers are a compilation of all types of numbers, we're emphasizing that they cover the entire spectrum of numeric values you might encounter. Understanding real numbers is fundamental because they form the foundation for much of mathematics and help us describe quantities in the real world. So, in essence, whenever you're dealing with numbers in everyday life, you're working within the realm of real numbers. Let's take a closer look at what comprises real numbers. When we talk about real numbers, we're referring to all the numbers that can be found on the number line. Within this broad category, we have several important groups. First, there are natural numbers, which are the counting numbers like 1, 2, 3, and so on. These are the basic building blocks of numbers used in everyday counting. Next, we have whole numbers, which include all natural numbers plus 0. 0 is quite special because it separates positive from negative numbers, and it's essential in many mathematical concepts. Moving further, we come to integers. These include all whole numbers and their negative counterparts, like -1, -2, and so forth. Then there are rational numbers. These are numbers that can be expressed as a fraction or ratio of two integers, where the denominator is not 0. Examples include 1, 2, -3, 4, and even whole numbers like 5, which can be written as 5, 1. Finally, we have irrational numbers. These are numbers that cannot be expressed as a simple fraction. Think of square roots that aren't perfect squares, or famous constants like pi or e. They go on forever without repeating a pattern. So, understanding these categories helps us see how all these different types of numbers fit together within the larger concept of real numbers, which is fundamental for everything from basic arithmetic to advanced mathematics. Let's talk about natural numbers. These are the counting numbers we use in everyday life. They start from 1 and go on infinitely. The key thing to remember is that natural numbers only have positive values, meaning they are greater than 0. There are no negative numbers or fractions here. They are the foundation of many mathematical concepts because they help us count objects, measure quantities, and understand the basic structure of numbers. So, whenever you're counting, you're essentially using natural numbers. They are simple but incredibly important for building more complex math topics. Let's talk about whole numbers. Whole numbers are essentially the natural numbers, but with one important addition: 0. So, when we say whole numbers, we're including 0 along with all the positive numbers. It's interesting to note that 0 is neither positive nor negative, which makes it a unique number in this set. All the other numbers in whole numbers are positive, which means they are greater than 0. This concept is fundamental because it helps us understand how numbers are categorized and how they relate to each other. Recognizing whole numbers as natural numbers plus 0 is a key idea that ties into our broader discussion of different types of numbers and their properties. Now, let's talk about integers. Integers are essentially a broader set of numbers that include natural numbers, 0, and their negative counterparts. Think of them as all the numbers you might use when counting, but also including the negatives of those numbers. 0 is a special, neutral number that acts as the dividing point between positive and negative numbers. So, whenever you see positive numbers, they have negative counterparts, like +3 and. This concept is important because it helps us understand and work with numbers in a more complete way, especially when dealing with situations involving loss, decline, or opposite directions. Connecting this to our overall theme, understanding integers lays a solid foundation for more advanced topics in mathematics and real-world problem solving. Now, let's talk about rational numbers. These are the numbers that cannot be written as simple integers alone. Instead, they are expressed as a fraction, where an integer is divided by another integer. But it's important to remember that the denominator cannot be 0, of course, since division by 0 is undefined. Also, for the fraction to be in its simplest form, the numerator and denominator should not have any common factors. Rational numbers have interesting decimal expansions. They can either end, like 0.5 or 0.75, or they can have non-terminating repeating decimals, like 0.333 or 0.666. These repeating patterns are a key feature of rational numbers. And here's a neat point. They are densely packed on the number line. Between any two rational numbers, you can always find two more rational numbers. This highlights how continuous and rich the set of rational numbers is. Finally, rational numbers are often called fractions, which is a term you're probably familiar with. Understanding these concepts helps us see the structure of numbers and how they relate to each other within the larger number system. Now, let's explore irrational numbers. An irrational number is a bit different from what we've seen before. It's a number that cannot be expressed as a simple fraction, meaning we can't write it as an integer over another integer where the denominator isn't 0. This is because their decimal expansions go on forever without repeating in a pattern. A key point to remember is that the roots of prime numbers are always irrational. For example, the square root of 2 or 3 cannot be written as a fraction, and their decimal forms go on infinitely without repeating. Understanding these irrational numbers helps us see the full spectrum of real numbers, especially how some numbers can't be neatly expressed as fractions, yet they are still essential in mathematics. This concept ties into the broader theme of understanding the different types of numbers and their properties. Now, let's look at some examples of real numbers. As you can see on the slide, real numbers include a wide variety of values. For instance, we have large numbers like 154,769,852,354, which can represent quantities such as population counts or financial data. We also see negative numbers like -8, which show that real numbers can be less than 0. Next, there's 49%, which is a percentage and often used in statistics or data analysis. The number 1.333 is a decimal, commonly used in measurements or calculations. The number 61 is a whole number, simple and straightforward. We also have a more complex example, 549.23789, which shows how real numbers can extend to many decimal places for precision. Then, a negative number with many decimal places, -5632.101010125685, illustrating how real numbers can be very precise in scientific or engineering contexts. And finally, we see pi, which is an irrational number. It cannot be expressed exactly as a fraction, and its decimal form goes on infinitely without repeating. The key takeaway here is that real numbers encompass all of these types: integers, decimals, percentages, and irrational numbers, and they're fundamental to representing quantities in the real world. This variety highlights how flexible and essential real numbers are in mathematics and everyday life, connecting to our overall theme of understanding the numbers that describe our universe. Now let's talk about the addition rules, which are fundamental for working with integers. First, when the signs are the same, we simply add the numbers together and keep the same sign. For example, if we have -2 plus -4, the result is -6. It's straightforward. Add the numbers and keep the negative sign because both are negative. Next, when the signs are different, we need to subtract the smaller number from the larger one. The key here is to pay attention to the sign of the larger number. So, if we have -2 plus 4, since 4 is larger and positive, the answer is +2. Conversely, if we have 2 plus -4 because 4 is larger and negative, the result is -2. Understanding these rules helps us handle all kinds of integer addition problems smoothly and connects to our overall goal of mastering integer operations with confidence. Let's look at some practice problems to reinforce what we've learned. These examples will help us see how to handle different types of addition problems involving positive and negative numbers. First, consider -4 plus 8. When you add a -4 to 8, think of it as starting at 0, going 4 steps back, and then moving 8 steps forward. The answer is 4. Next, we have -1 plus -3. Since both numbers are negative, you're moving further back from 0 by 1 and then 3 more. So, the total is -4. Finally, let's look at 5 plus -7. Here, you're starting at 5 and then moving 7 steps backward because of the -7. Since 5 minus 7 is -2, the answer is -2. These practice problems are great for solidifying your understanding of adding positive and negative numbers, which is a key part of mastering this topic and connecting to our overall goal of working confidently with different types of numbers. Let's talk about additive inverses, or opposites of two numbers. The key idea here is that when you add a number and its additive inverse, the result is 0. For example, the additive inverse of 3 is, when we add 3 and we get 0. So 3 plus -3 equals 0. This concept is really useful because we can use additive inverses to simplify subtraction problems. Instead of subtracting, we can think of it as adding the opposite. This helps us understand and handle equations more easily, especially when solving for unknowns. Remember, the additive inverse always pairs with its original number to make 0, and this idea is a fundamental part of how we work with numbers in algebra. It connects to the overall theme of understanding how numbers relate and interact, making complex problems more manageable. Let's take a moment to understand the difference between subtraction and adding a negative number. For example, if we look at 7 minus 3, that gives us 4. Now, if we consider 7 plus -3, do you see what happens? That also equals 4. So in both cases, the answer is the same. The key difference is that 7 minus 3 is a subtraction problem, while 7 plus -3 is an addition problem. This highlights an important concept. Subtracting a number is the same as adding its opposite. We often call this the keep-change-change method, meaning you keep the first number, change the subtraction sign to addition, and change the sign of the second number to its opposite. This idea helps us see that subtraction and addition of negatives are closely related, which makes working with negative numbers much easier once you understand this connection. It ties into the overall theme of understanding how numbers behave, especially when negatives are involved. Let's talk about subtracting integers. When you see a subtraction problem, remember you can change it to an addition problem. The key idea here is the keep-change-change rule. First, keep the first number the same. Then, change the subtraction sign to addition. Lastly, change the second number to its opposite. If it's positive, make it negative. If it's negative, make it positive. After that, you just follow your addition rules to solve it. This approach makes subtracting integers much easier because you're really just adding the opposite. Keep this in mind as a helpful trick to simplify your work with integers. All right, let's look at some examples to clarify these concepts. First, consider example 1, -4 minus -7. When we see a minus and a negative number inside the parentheses, it can be a bit tricky at first. So we rewrite it as 4 plus 7 because subtracting a negative is the same as adding its positive. Then, since the signs are different, one is positive and the other negative, it tells us to subtract the numbers and use the sign of the larger absolute value. In this case, 7 is larger, and since it's positive, our answer is positive 3. Now moving to example 2, minus 3 minus 7. Here, both numbers are negative and the signs are the same. So instead of subtracting, we add the absolute values, 3 plus 7, which gives us 10. Since both are negative, our answer is negative 10. The key takeaway here is understanding how to handle signs when subtracting integers. If the signs are different, we subtract and take the sign of the larger absolute value. If the signs are the same, we add and keep that sign. This rule helps us simplify and correctly evaluate these kinds of problems, which is a big part of mastering integer operations and connecting to the overall theme of understanding integer rules clearly. All right, let's talk about multiplying and dividing integers. The key rule to remember here is about the signs of the numbers. When you multiply or divide two integers, if the signs are the same, meaning both are positive or both are negative, the answer will always be positive. So for example, positive times positive gives a positive, and negative divided by negative also results in a positive. On the other hand, if the signs are different, one positive and one negative, the answer will be negative. That's true whether you're multiplying or dividing. This rule helps us quickly determine the sign of the result, which is essential as we work with integers in more complex problems. Remember, understanding this pattern is a big part of mastering integer operations. Let's take a moment to practice multiplying and dividing with different types of numbers. First, look at minus 8 times 3. When we multiply a negative by a positive, the result is negative. So minus 8 times 3 gives us. Next, we have minus 2 multiplied by. Multiplying two negatives actually gives us a positive, so the answer here is 122. Finally, times 6 is a negative times a positive, which results in minus 18. These examples highlight some key concepts: multiplying negatives and positives, and how multiplying two negatives results in a positive. Understanding these rules helps us confidently work through more complex problems. Remember, practicing these kinds of calculations reinforces your understanding and prepares you for real-world math challenges.